Hola. Okay. Hello, everybody. Today we're doing JavaScript parser combinators. I got my little girl Sabine here with me in the audience. She's gonna keep me on track. She's 6 years old. I'm sure she'll know what to do. All right. I just upgraded Node. I have Node version 21, so that's JavaScript runtime. And I started doing this, and got about a couple things in, a couple functions in, and I realized, hey, maybe I should record this. So that's what I'm doing. So let's switch over here. All right, this is a spreadsheet I made when I was just looking over my Python and J implementations of this. And the question was, I'm working on a language that I wanted these parser combinators. I'm doing a course on these parser combinators, or a very small course, a mini course. I'm going to make a video about it. Other than this video, this is a live stream. I'm going to make a scripted video, and this is like a rehearsal and dry run. And so I just want to get all the steps in. And JavaScript happens to be a pretty good language for writing these little functional combinator kind of things. You can get a lot of what you get out of Haskell. This is probably not the way your favorite teacher would teach you how to write JavaScript programs, but unless I'm your favorite teacher, so which would be funny. But here you go. All right, so basically the idea is that we are going to make a parser combinators. That's this stuff over here. So in this notation that I've put up here, D is some data type, S is a state tuple, which is the state of the parser. P is a function from state to state. So parser is a function from state to state. C is a character in the alphabet you're parsing. So usually a character or Unicode character, or in the case that we're going to get up to in my system, you've got lists of symbols and stuff like that. So it's a symbolic programming language. And T is a text in that, a list of characters in that alphabet. Hey, baby Sabine, say something, baby Sabine. Okay, we cannot hear you at all. So your microphone is not picking you up. Sorry. She said, yeah. She was also humming behind me. And so that is why I wanted to see if she was coming up on the microphone. Okay, anyway. Okay, that's going to distract me, sweetie, if you would please not do that. Okay, so we're going to make... Cannot read yet. Can you read? A little bit. She can read some. So she does not know what's going on here. But if you watch on the screen, maybe that'll make some sense to you. I don't know. Maybe not. Not just go home, okay? Go downstairs. All right. Anyway, so the idea is that we're going to make... you don't have to do this in JavaScript. You can do this procedurally, do all these assignments and whatnot. But I wanted to make these and just see how it went. And it looks like it's going to be kind of fun. So... yeah, I started doing this, and then the parse state is going to be this structure right here. So in J, I did it as a just an array, of course, because you don't have dictionaries. But JavaScript, we have dictionaries or objects, and so I'm going to make this an object. So these are the keys of the object. This is the values of them. The match bit is a Boolean, 0 or 1. JavaScript has true and false, but I'm actually going to use 0 and 1 because of this combinator here, forward, where you take an integer and you move forward n times. So based on the, maybe we'll see. I don't know. Maybe we'll just cast it to an int or something. Anyway, so we have these keys. So let's just take this, and I copy this. Will it paste into a... So if we say state 0 is going to be, all of these are just going to be empty. Or I guess, so this is going to be a function. And I'll copy all this. Oops. That was the old thing I had. I was playing with this, and I got to functional programming with zip. All right, so let's say a little more verbose than I'd like, but we could say that the match bit, because I'm gonna have to copy this. All right, I guess, what we could do? We could just return a dictionary. So rather than do that, we just say match bit is going to be 0. Input buffer is going to be an empty string. The current character is going to be that. The current index is going to be -1. The mark is going to be -1. Tree builder is an object that builds trees. I don't know that we need it. That rattle on. We need it in J because of something. I'm going to leave this out for now, and we'll put it in later. Bye, sweetie. All right. So if we call S0, we get this dictionary back. So I'm going to leave out the tree state and the tree builder for now. So we'll say this is parser combinators in J. All right, so she decided that was enough for her. All right, which I don't blame her. Okay, so we got the match bit, the input buffer, the current character, the current index, and the mark. And I think is on a keyword? Yeah, on. Oh, no, it isn't. So in JavaScript, you can say like for x. Oh, you say of. Okay, so on is free. So the word on is free. I guess I was gonna call it oi, because I thought the word on would be wrong, but so the first combinator, so that was S0, is just initial parse state. This is our initial parse state. So we're not matching. We have an empty string to consume. We have no character. We're looking at nothing yet because we're before the start, and the mark is before the start. So the mark is going to be like the start of a token, and then the index is where we are right now. Okay. S0 is the initial parse, and by the way, this is all coming from pegs. I specifically have been adapted Alessandro Worth's Ometa 2 paper, but it's just pegs in general, and I renamed some things, and all the stuff in the middle is just my take on it, how I've come to implement things. Okay, and I'm going to close the door now because she left, and so I'm going to. Give me a little heart. Okay. Half a heart. The other half is on her sister. Okay. Okay, so the word on takes an input buffer and initializes the parse state. So it puts us at the start of the state. Okay, so on is going to be a function from a state. That's going to return a new state. And what we want to do is we want to make a copy of the state. We're always going to make a copy so that we can backtrack. We're never going to mutate anything in this program. So let's see. What we're going to do is we're going to make something that looks probably like this. It's going to be like MB of 1, or sorry, no. I'm going to set the index to 0. We want to set the character to S0. And we want to set the index. So the index is 0, character to S0, and the IB to S on S0. Does that match? Yeah, that matches. Jay has a much nicer way to say this, but this is JavaScript, so this is what we do. We're going to have nested calls here. So, of course, those functions don't exist, so we can't actually run this yet. So we got to say this is like to do. This is our goal. Oh, sorry, that's it. To do. So we need to make ix ch. We're going to make accessors for all these things. And the way these accessors work is they're going to take they're going to take a value. They're going to take an index and a value. Okay, given a key, they will return a function. And then we say if, and then we say assigned. No, assigned is not a thing in JavaScript. You say if v is undefined. So it's going to be both a getter and a setter. If v is so get or set is the thing that takes a key and returns a value. Sorry, takes a key object value. Yeah, so takes a key, returns a function that takes an object and a value, possibly, and if the value is undefined, it's going to return. It's going to act as a getter, and it's going to return OK. And if it's not undefined, if it's filled in, if you give a value if you pass in a v parameter. That sucks, because you want the v to be first. But so if it's two parameters, so x, y, we'll call it x and y, right? In J, it's it's clear which one it is. But if if y is undefined, then we're going to get k. We're going to take x and do the key. But if otherwise, if you give two parameters, then we're going to say set. We're going to assign something. So we're going to say set x, y, or key to the value y, something like that. And I think we even need to say this. Okay, but we don't know what set is. So set is going to take an object and a key and a value, and then we want to copy that object. So we can do that with, I think it's called splat notation or something like that. Splice notation. So probably that's a copy. So let R equals a copy of this, copy of O, and then RK is equal to value, and then return R. And then this is get set. So here we want to set y ax. Little clunky. Right, because you either want to, right, based on whether it's two arguments. So GS O so GSK O is O.K. And then GSK OV is set OKV. Is that right? Nope. not, it's VO. And the reason we want VO is so we can write it like this. So we can put the name, we can nest it like this, and we have a chain now. So we can start with S0, and we can assign IB as S, and we can say CH is S0, and IX is O, and otherwise we'd have to write it like IX, CH, IB, S0, S, S0, where this is just stupid, right? You want the values next to each other. The odd order is so that the value can be right next to the setter, and we get a pipeline. We get something like a pipeline with a bunch of parens on the right. Okay, so that's that. Like ideally you wouldn't have these parens at all, but I don't know how to make that. That's function composition, and that's not an operator in I mean, I guess we could do that. We could implement that, but we'll save that for another day. What you would do is you write like, you know, compose, and then you would say like, you know, you would write IX0 and then have that return a function, and then CHS0 have that return a function, IB S, or sorry, IB S and S0. And we would say like pipe, or, you know, JK or something like that, left to right. I don't know what you'd call it, like APL, Iverson expression. How about X? So you call X on this, and you could even do it like this. How about functional expression? Function J style functional expression. How about just JK? Could I do that? Do I want to do that? Is it worth the time? I kind of want to do it. All right, so what does that do? So we would say and if you did that, you could even remove the parentheses. Like we could do it like this, IX. And just say, is it a noun? Do this. If it's a, I don't know, whatever. Kind of nice. Do I want to do that? Maybe we'll put that in the to do section, which it is in the to do section. Okay, so to do. Like it just, this is actually fine. You just have to worry about balancing all the parens. So you don't have to balance the parens. So you don't have to balance parens. So maybe we'll do that at the end, if we have time, which I probably will. Okay, so back up here. So now we need to make these getters and setters. And so we have them, and so we say IX equals GS IX. And so now let's do this. So did we run any of them? So set. So if we say O is equal to some function or some dictionary, and we say set O letter X and then 5, then we should get that, and then O should be unchanged. What we want. So that works. GS is in this, and so we say we'll actually implement instantiate one. So IX, and we say O, no 5O. There we go. And if we say, yeah, IX3, IX2, whatever. So there we go. And we may probably need to say let on all these things. We don't have to, but. Right, so this is general struct helper. Let and then these are actual parse state. And we're going to have a couple more of those little helpers in a minute. Let's go all the way to line. We'll do line 50. These are going to be short. Call this to do. All right. I don't know why I do this. I do it so often. Maybe I should have a macro for it. Okay. So these are the constructors. You could probably do this with a little bit of metaprogramming, but let's take this. So MB, IB, CH. We already have IX and MK. Okay. What? And I'm just going to record a little macro, and we're going to say record it or copy it equals GS, and then down here, and then we'll say F4, 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 F4. I don't know if that's standard Emacs or if I just assigned it, but I think it's standard Emacs. Go. So now we have these getters and setters, and S0 is. And I'm going to go ahead and put the comments about what they are for each one. So this is the index into input buffer. Let's do it like this. So match bit input buffer, index into input buffer, current character, just a cache version of IB IBIX, and that actually could be an accessor. I mean, we could just write that function because you'd probably never set CH. In fact, we could do it that way. Except in this state, you're at the end or whatever, so maybe it's okay. All right, mark is the number. Start of token. Start of current token. Index of current token, and we'll have more stuff later. Okay. So now, just out of curiosity, can we beat the? That's pretty compact. There's no spaces there. So can we beat that? So can we say So I don't think we can. I think it's actually longer to do it this way. IB, or maybe it's exactly the same. X negative. No, it's probably going to be a slight. It's going to be like 1 or 2 characters longer. 1 character longer. Oh, plus all the end parens. Okay, so yeah, it's actually it's longer because of all the end parentheses. But I bet this works the same, and we can actually remove one layer of the parentheses. And if we do it like this, we can remove 1 paren, but MB is not defined. Oh, because I haven't run this. And then when we do the, and then it works. Interesting that it's backwards now. But it doesn't matter. Okay, so obviously this is easier to do from the start, so we'll just get rid of it. Get rid of that. Like this is just more so we can, you know, also the second version is wasteful because you're copying it for every setter. It doesn't really matter because it's just the initial state. You're going to call it once at the start of the parse. Okay. All right, so we've done that, and then now, all right, so the idea is you say on text to parse. There you go. You get initial parse state. So you as t, the match bit is 0 because we haven't tried to match it yet. The index is 0 because we're at the start around the t, and then we haven't started a token. So there you go. So then we're going to be able to say, like, you know, the idea is you're going to have like grammar, you know, some language on text to parse. So you're going to pass in the parse state, parse some language, or you know whatever. That's the idea. So you know, like rule, basically, you're going to give it a rule on text to parse, and that's how this is going to work. And it's going to return a state, right? So a rule is going to be it's going to take a state and it's going to return a state. And this is the ID, the identity rule. It does nothing, right? So I was trying to press, yeah. There you go. So that's how a parser is going to work. That's a parser combinator. This is the simplest parser. And then I'm going to make 2 more here. So one is called M1 and M0 because these are the most, and so this is going to be M0S. These are like the most common things. We're going to either match or not match. So like, right, so oops. So match, fail. All right, so these are the, right, parse state. All right, where are we at? So we have S0, we've got on, NX. Okay, so then I'm gonna look at the J. I'm porting this from J, so I did a review of the J version of it. I really liked how this worked in J. You can actually compare it to contrast, I guess. Weird color scheme. I think everything is being treated as a string because of the terrible way the J Emacs mode works. Hang on a second. Can I get the? Forget if I have a J mode for Visual Studio. I think I do, and I think it works a lot better. Give me 1 second. If I can make this. So file, Cinder. Yeah, much better. So all in some other repository. So it's a pretty long file. It's very mathematical like this, and you can see it's got a bunch of example parsers. I'm kind of porting this, and it should be, this is J-style JavaScript now, close as I can get. Exactly the same stuff. We're going to get a state and tree builder later. I know this is my M1 and set the match bit. I changed some of the names. Okay, so I forget. I wanted to show, I guess, the corresponding code in J or something. I guess on is what I wanted to show. Yes. So I said, as I actually have S0 being a thing. So here it's a dyad. So say on takes a string y and takes the first letter of y and puts it in the ch, and we just set the index to 0. Oh, so I set the index to 0, and okay, so they're both 0. All right, so in J I did it a little bit different. Probably this is actually probably more correct. Whatever. Okay. So what's next? Well, rather than just copying it, let's like deduce why we need these things. So the first thing we want to do now that we have a parse state, we want a rule that takes called emp, and it's going to take a parse state and it's going to return. It just always matches. So the empty string, it's like if you want to say like any whatever match is, and it's always going to match the empty expression, right? Yes, it is. Like that, yeah. See, that matches, and then the empty string matches. But whatever it is, it's always going to match at index 0. This is this is a regular expression that says match the start of the string. Everything has a start. Everything has a start, so that's empty, right? So that's the empty expression. In fact, you probably just even say like this. Cannot say that, okay? Because that's a comment. Right, well, anyway, you can match that. Whereas you cannot match the end of the string, right? So that's not right. You can always match the start. So that's emp. Right. So emp is going to be it's always going to match. So it takes a state and it returns 1. So emp is just M1. Oh, but I haven't defined it. So yeah. So if we have S0 and if we have M1 of S0, reference error M is not defined. Match bit. Okay. So there we go. So again, S0 is that, and they're all the same except the match bit has changed. So that's all we want. So that's emp. Emp is just M1. All right, so parser combinators, or parsers. I guess I should move this to the top, so closer to the top, I guess. Parser combinators. You can't scroll one. I don't have the scroll bar in the terminal. Sometimes what I like to do is put like this thing. Now we can page through it. So let's do that. All right. So parser combinators in J, and then we'll put general. So page 0 is parser combinators. Page 1, general struct helpers. Page 2 is parse state, and page 3 is parser combinator. And all I'm doing is pressing Control Q, Control L to put this in here, and then I have a macro and Emacs. This is the form feed character. I have a macro and Emacs, and also actually made a plugin for VS Code that lets you page through this way. And most languages allow you to have this is a white space character. It's recognized as a white space character. The GNU coding standards even tell you to put this in. Okay, so the parser combinator is emp, and emp is m1. Match empty always matches. Students nothing. That's emp. So then the next thing over here would be any, to match anything. Okay, so any is gonna let's try any it takes this parse state, and then it's going to move the index forward one piece. So we can take the index of the state, add 1 to it, so we're going to say, so index is going to be 1 plus the index. I think we actually need to refer to this, right? So we say let I is equal index plus 1. And then we can say ix is going to be I. Ch is going to be the input buffer of S at I. First, we are matching, so the match bit is going to be 1. The index is going to be I. Ch is going to be the input buffer of S at I, of the state at I. And that's it. Of S. Close Ch, close Ix, close MB. And then return this. What happens if you try to match to any string? So any on, what happens here? Undefined. So your character is undefined. So if I let's even do it like this. Okay, we'll say C is equal to IB of S at I, which is what I find here, CH is C. And we'll say if C is defined, then we'll return this, else MB or M0, we can even say M1 of this. We can return M0 of S. Okay, so any on that did not match. Oh, right. It's because it was undefined from the start. H is undefined from the start because we never had a first character. Right. So that's good. So then we say any on. And if we just want the match bit, we can say is the match bit. No, it did not match. But if we give it a character, oh, that didn't work. That should work. Works. Okay, let's debug this. So to debug it, we'll just take this out of this, and we'll say s equals s s0. That all works. So what C is undefined. It's because I've already added 1 to it. So instead, we want to say more like so we'll say like B equals IB of S, I less than B len. If I is less than B length, then yeah, and that's our condition. Then we match, and we say the index is I plus 1, and this is B I plus 1. Because we got the buffer already. We have it as in a variable, right? So S is going to be on X, and then this we did return 1, and if we say right, so then we call this. This whole thing is an expression now, so we can just say the linter will not be happy with this, but this whole thing is one expression, so we can say we call it any equals S. So there you go. This is also meant to be an answer to the question, like, how can people like Arthur Whitney write code like this? Well, because you write very small functions, and yes, it's going to be unreadable when it's in pages of text, but when you have it in the thing here, it's cramped, but it all fits on one line, and you can test it and experiment with it and paste it in. And How do you do it in C? I guess you don't do it like this, but this is a doable, right? Okay. So now we have any matches this. I'm sorry, any on this. No, but any on this. Yeah. Ooh. Now why would that? It's possible that you can't do these assignments inside of this. That returns a match bit of 1. But when we say any, okay, so then we have to say, hang on, just verify the. Yeah, that shouldn't return that. That should have returned a function. All right, so I'm doing JavaScript wrong. We do have to do it like this. And so now the linter will be happy again. That's why the linter is mad, because there we go. That's what I want. So then go up 2 lines. Okay. So we matched. We do not match. But the character did not get set. So let's test any on any on that. And just return both. Why is it why is this returning -1, right? So I is ix of -1, and is it I is less than b ib. So we'll say s equals s0. Ix of s is less than ib of s, right? Sorry, length. True. Therefore, m1 of s, yes. Okay. ix, I plus 1, so I is -1. I equals ix of s, right? I plus 1 on S, right? That works. And then we're going to say PHB I plus 1. This should be a copy, so this should not, it shouldn't have anything to do with the fact that it's. Why is it? But I equals IXS, take the index. B equals the input buffer of S, take the input buffer. If I is less than input buffer length, that should absolutely. What happens if you do this again? I'm just curious if this, like something crazy could be going on here. But it shouldn't. I just want to see. Come on. I hate these prints. S0 M1 on any. S0 M1 on any. Okay, that is wrong. Okay, I don't know what I'm doing. Say on. Oh well, maybe that's maybe that's what I'm doing. Maybe that's the problem. Yeah, okay, so any on. That makes no sense to me. Am I that? That's right. No effect. On. Wait, what? Oh, it's because on is wrong. On is wrong. On is setting the index to the first character. All right. Let me look at what I did in J. Let's look at J. We do start with the index at 0. Okay. And then next is what we're about to do. So move to next character. We're going to say I is equal to 1 plus the index of y. Yes. And then this is I again. So index is put index into y, and then put the first character in I index. This is redundant. I think this is, I think if you get the first 1 plus the index of I. This is just getting the index, adding one to it, modifying it in place. Oh, so when we say on here, I see. So the index is 0, but you don't actually get it yet. So okay, that's what I'm doing wrong. So then we say any on that, but any on that, we move to index 1. So the index is right after the last character, right after the character that. And it looks like the mark is also there. No, sorry, the match bit and the index are 1. The match bit, index, and the mark are 1, 1, 0. See, it's so much more expressive in J. But we should be able to do this. Okay, so then the trick is I'm somewhat confused why that works. Oh, so if you say ix 3ix as 0, oh, it returns that. Say 1 plus, so y is equal to s0. If we say 1 plus ix y, that's 1. Okay, So I is what? 1. And then we say y again. Now we're back on the original state. Ch ix. That's assigning ix to 1 plus ix of y. What? I see. So this says if the index of y is less than, okay, so yeah, so in this version I do it without adding the 1. So let's do it that way. This is not an error with the syntax. This is an error in my logic, right? So this is not a problem that people are going to say, oh, you're writing it too terse and cryptic. No, that's not the problem at all. The problem is the rule is wrong. Oh, well, hang on. This right here can be rewritten in terms of this thing up here forward. We can say and then we can say just algebraically we can say we can reverse these and get rid of this. So in J, that's what that would. Which, if you really want to do it tersely, you would be, yeah. Oh, just do it. It'd be forward. It'd be forward lengthen IB is greater than IX. That's it. You can write it that way. Okay. That's all mathematical. But like NB test this. I think that's right. If you wanted to golf things, I guess. So let's break this down. So let's do NX is a state. Takes a state and it returns. It basically does that. Let I equals IX of the state. and b equals ib of the state. And we're going to return this is exactly the same. I don't set the match bit here. So just move to the next. So forget the match bit. And it doesn't even check this. It just says that I equals 1 plus the index of that, and return so set the index to, again, this is, let's rewrite this the way it should be. That should be the same. That should say C. Whereas in J, what do we get? Let me see if I get the right thing in J. Wow, I've got so many windows open. Huh. I can't even jump to the end because I can't, I don't know how to type. What am I in? Vive. Don't need this, don't need this, don't need this, don't need this. Yeah. Okay. Even then, I forget how you renumber windows. Okay. Okay. Are you kidding me? Okay, sorry about that. Should have prepared my windows a little better. All right. So the whole question was, what does this look like on ABC? And then NX, B, and NX is C, and NX. All right, so it is wrong. I'm still out of sync here. So after two of them, I should be on C. Is that right? 0, 2, C. 0, 2, C. So index is 2. Yeah. They're out of order, but. Okay, so we're consistent at least. When I do this, I need to have tests so that I show exactly what the state should be. And I will have tests. So maybe I should record the test right now. Maybe I'll do that. So we'll say test. I'll just record it as a test. So, oh, whatever. Give me 1 second. I have to run to the restroom. Yep. When people ask me how I did this in 10 minutes in the speed run, they will look at this and they will say, oh, okay. It's not so. This guy's not a super genius. This guy just rehearsed. But the point of the speed run in the future will be to show you the path to do it so that you can bootstrap something as quickly as possible. Leave a trail, right? To get to the next point. Right, is this actually correct? S0 0, 0, 0. That's not correct. Then why do we get the same results? We say I pasted in exactly how I wrote it. Right, and I said this. Oh, actually, this one is this version of the file is not doing the thing where it makes everything a string. That's good. So I'm pasting this in here. Same. So now it runs with this line, and that's the same. And X on cat should return A. Okay. And the index should be on 1. And here if we say nx on cat A, and the index is on 1. X is on 0. X is on 0. Yeah, that's right. Okay, so we're good. All right, so nx to string is this, and let's just put that over here. Let nx equals this. Okay. Move to next character. Then forward is something that takes an integer and a parse state, and it's also going to take a boolean. So it's boolean. So we say int true and get 1. Integer true. 0 plus true is 1, and 0 plus false we say plus false plus true. Yes, okay. We don't. So it's cast to an integer. Just so say plus I. I'll say n times, and then let's say for let for I think we can reassign for let I equals 0, I less than n, I plus plus, or even say I plus plus less than n. Say s equals nxs. Return s. I less than n, I plus plus. Okay. So if we say forward true s0, s0 parentheses, and that works. All right, so this is forward. But we're going to do plus n right there to make it a Boolean. What happens if we do forward true S0? Forward false S0? Oh, so you don't even have to do that because I is less than true. So 0 is less than true. 1 is less than true, false. Okay, so we don't even need the plus. We can just do that. Call nx n times. N may be Boolean. Nice. We could put a space in there. To me, it doesn't matter that there's a space or not. Like, I don't know if people. Okay. How about that? I don't see that it's making it more readable. But I'm used to looking at J, so what do I know? And fourth and things like that. In fact, it kind of bugs me that that's there. Okay, so to any future employers, I'd be more than happy to follow whatever coding standards company provides. Whatever. Okay. Boolean. N may be Boolean. Okay. So now let's see what happens with any, right? Any needs to be rewritten in terms of these things. Now we can say any equals take an S and return. I think we do want to do this first part. Oh, but we decided this doesn't work. Let I equals IXS. And then based on this, so then we can say forward. And because we're doing that, now we can just say IXS is less than IBS length. And then this whole thing reduces to this. So we say any on, oops. Let's see what that returns. On false true. Okay. Oh, so forward's wrong. Forward has to be wrong. Return S. R equals S. Oh, because I didn't give it a number. That's why. So it was not that. This, I do think that makes it more readable, but I guess we could just leave it if we're going for compression. Does it make it more readable? I don't know. All right, so forward 1 on S0 should give me the same thing, and if it does, I'm happy. Okay. Which should be the same as NX on cat. But for 2 on cat would be put you on the T. Okay. So then here, any equals this S. So any on, nope, match bit is false. Any on this, match bit, oh. All right, so we have to say let so we're going to set that to int, so plus m on forward ms. Or we could even say, yeah, that's fine. What am I missing? Curly brace. Right, because that's correct. That's good. And then any on this should be 0. Match bit is 0. That's right. Any is good. Match any token. Fail at end of input. Okay. All right, so now we can match the empty string. We can match a token. So we've got the, this, and we've got a dot. Let's go back here. Let's look ahead. We've done this. We've done this. We've done forward. We've done next. We've done on. The only thing missing is look ahead, and then we'll have all those. We have all these, except for the TB and TS because we haven't done them yet. All right, so we're up to neg. So neg, it never matches anything. It's a look ahead. So in JavaScript, you can say, in JavaScript's regular expressions, you can say question mark bang xxx, or say x dot. So then you can say match. So that does not match. This does not match, but this matches. Okay, so it matches anything but an x. XO fails because there was an X prefix. So that's what we want to do. It doesn't consume the X if it's there, and if it's not there, it just it's just looking ahead. So that is neg. All right, so let's look at how I implemented neg in J. Neg. Oh no, we haven't done that yet. Neg is just invert. Okay. That's I misspoke. The word what I was describing is called not down here. Neg is just invert. You almost never use that directly, so that's why I don't think about it. So neg is just takes us to parse state, returns a parse state. So we're just going to be mb 1 minus mb of s on s. So neg any on x any on x. So any on x was that, and then we just negate it, and there we go. And the same thing, any on this is 1, not is that. Right, so we'll put a test here to remind myself to test. Anyway, neg is, let's just copy it. Any match any token, fail at end of match any character. I'm using the word character to refer to tokens in a list, even if you're matching lists. This should work completely fine for lists as well. We can test that. There you go. The input buffer is 0, 1, and the character is 2. Should work totally the same. Okay, which is going to come in really handy if we do it. So neg is easy. End is easy. End s end. If we had function composition, it'd be super easy, but not. Oh, sorry, neg any No, this is wrong. That's not what neg is. Sorry, hang on. Neg, it takes a parser and returns a parser. And a parser is a state to state. So we have to, it's a higher order function. Because neg should not consume the, should not consume the x. So neg any on x, you see it set the index to 1. It should set it back to 0. So what we actually have to do we'll say let f flag, or even b, equals match bit so sorry, it takes a parser and then returns a new function. So we're going to close over that function. So it's an adjective, so it's a higher order function. Let b so b is going to be the match bit of applying p to s to the state. We don't even have to name this. We can just say mb 1 minus this of s. right, so now neg any on x. But what I want it to do is have this be exactly the same, except the ix should be 0. All right, neg any on x. This is the proper syntax. So this neg any on x neg, right, that's right. I think we can save this, right? I think we can save a little bit of stuff that we did. Yeah. So on can be a little bit simpler. That's the only one we can do it for, I think. Neg any on x. Gonna give us that. Oh, that's wrong. Look at that. Input buffer, it goes into did not know that. Okay, so that does not work. Glad I caught that before I did that all over the place. So we'll live with it. Neg any on x. And see, now you're seeing the separation, right? Like the parser goes over here, and at the end you're gonna have one function, and you're gonna call that function on x. This is gonna be the pattern for all of them going forward. Everything going forward. Hot in here, got a little heater under my desk. Okay. Usually cold. So that the code is wrong here because I didn't copy the new version. Right here. Okay. I feel like if I made this little functional programming thing, like all these would be a lot simpler. Whatever, doesn't matter. Oh. All right, so then I was about to do something else. Oh, end, right? Then end. Is that neg any of s. But then you can just say end is neg any. So then end on is 0. And on that is true. So we match on true. That's it. So you don't even need, so you see you're composing functions now. We have a way to compose functions. So that's it. Okay. End matches end of input. Okay, next. Character A. Okay, so we have a CHR and we want to match, you know, like A on A, and that should match. So what is CHR? Well, CHR is going to be going to take a character, an alphabet character, a C. We'll call it C. And then we return a parser. So we return a function that takes a state and says it's going to be forward look ahead. Look ahead S. Look ahead of the state. Look ahead 1 of the state is equal to C. I'm wondering if I should put that. I'm repeating the logic of this. Repeating the bit here. Let's make a new thing called forward M. Forward M. Forward match if n is greater than if n is greater than 0. N shares if else fail. So this is brand new, on the fly, never been seen before. Forward match. And it takes a number and then does this. MB match bit is going to be plus of n forward ns. So we have to have a state. But wait, is this? This is one of these things. Right? So forward match. And now we can rewrite this as oops, I didn't want to change that one. I just wanted to change this one. So forward, where we say ix of s is less than id of s. So if the index is less than the dot length, if index is less than the input buffer dot length, then move forward. So you use the Boolean as the number 1, and you move forward 1 character. There you go. So just double check any on return 1. Nope. Because I didn't say forward match, I said forward. Forward match. And forward match is this. Any on x. I was thinking about whether I should collect a test suite. I have a test suite here. And so I'm going to, in the J version, I guess, here. So the J version has a complete test suite, and I'm just going to turn that into the test suite. So I'm not going to worry about that. I'll keep collecting these things. when I write this test suite, I'm going to go watch through this video, see what I did, make sure I leave a clean path or whatever. I like doing this where I leave like the longer version and the shorter version. Again, leaving a trail, like introducing a rationale for why I have FWM. All right. So end is neg any, and end on x should be false, and 1. So what was next? Character was next. All right, so now the thing would be to look ahead. And so look ahead. You say concat? Yes, and you can say this concat that, and you can say this concat that. This works good. So so what I'm thinking of will work fine. So character will be what? Why did I just do that? It made sense in my head. There was a connection in my head. I don't know what it is. Maybe we'll see in a second. So it takes a character and returns a parser, which is a state to state. And this state is going to be what? What are we going to do to that state? We're going to do a forward match on the state. If y, what do? We say, oh, I'm not sure why I did it. Format C equals, yeah, I think I was just doing that for silly reasons. So input buffer of S at ix of S plus 1. So if we say CR of X on XYZ, I expect that to match and consume one character. It matched, but it didn't consume it. It didn't match. Oh, because I don't have to do the plus 1. Yes, that consumed it. And then if we put like this, Control T doesn't transpose. Right, this is right. So if we change that, to this, then we're looking at the O. We're on index 0, right? But if we change it to an X, then it matches that X and moves it forward 1 to the Y. That's perfect. So there you go. Now I see that's cryptic, but it's like looking at mathematical notation. This is a mathematical notation for parsers in JavaScript, and I think it's a perfectly reasonable way to write programs. And people are going to look at it and say, "Well, how do you write programs like that?" They're going to say, "Oh, that should be a C." Okay. I would say if you try writing programs like this, you might write better programs that'll be harder for other people to read, but work better. I don't know. Match a single character. Now, can you say, okay, so now I have a question about this. I don't, so the next one is going to be CHS, which is going to be choose. It's either choose or character set, right? Choose or CS, right? CHS is choose or character set. Either name. will be the same, and it's just gonna be the same thing. It's gonna match one character, match one char if it's in CS. Hi Kyle, don't forget to change the forward to in any definition of your code. Oh, thank you so much. Yep, you're right. Thank you. That's the problem with this. You run it and then you don't have tests, and then yeah. So I do plan to go through again, but thank you. Because now I'm just living off the state in the REPL and not in the Actually, can I? And thanks for watching, by the way. I didn't know anyone. My control panel tells me nobody is connected, so I didn't even know anyone was here. Usually it says how many people are connected. So thank you, Kyle Mitchell. Choose character set. Match one character if it's in CS. Okay, so this is going to be. It's going to be CS contains. Is it contains? ABC contains? No. Index of. Yeah, but there's like something. I could have sworn I looked this up like just the other day, and there was something other than index of. Includes. And if you say includes, X includes true, this does not include true, and this includes, oh. Right. Right. So here, I'm calling them characters, but I also wanted to match for like symbols and strings inside of a list of strings. All right. So includes CS includes that. Let's see if that works. So character set ABC, and then the state would be on Apple, and that should match one character. Match one character, and then if we change it to Apple, it should not match any character because it's only on the first. If we change put a Z in there, then it should match again. Okay, so that's good. And just so that's that. That works. I don't know why I needed that try thing. It's an error capture, but I don't think why that's introduced next in the J version. Oh, what happens if we're at the end? It just doesn't match. I think in J that threw an index error, and that was the problem. And so I needed that try thing to catch the index error. Whatever the Oh, right, because you gotta say on. Right. I am actually not sure why that. I don't know why I need to try there. Not sure. But I'm not going to worry about it. So I think I don't need it here. It's literally just a try like catch thing. So this is basically if the thing this would be like you put an F over here. So it's a conjunction, and when you apply it here to O is just going to set the match bit to 0. So that's what I'm calling M0. It just if the function fails or the verb fails, then reading past the end of input. Yeah, I don't know what. Oh, I bet it was because I had a look ahead before, and I changed. I'm almost positive now that I originally wrote this where you're constantly looking ahead one character, and I just said, well, just set the state to the current character and the index one thing behind it. I don't know. Anyway, okay, so sequence. Okay, so now we're at the fun part. So now what happens when you combine these things together in a sequence? So the sequence is going to take a bunch of parsers, and it's going to return a new parser. And you're just going to loop through them, but you have to say so really just for let I equal 0, I is going to be less than ps.length, and you say I plus plus. S is going to be ps of I, apply that to it's up to S, and then nope, because we need to be able to backtrack. So we say let R equals S. So then we're going to say R equals this. So we keep applying it to R. And then if this is going to be my first two-line multi-line combinator here, but if hope I can write that. So if the match bit of R, so right, if not the match bit of R, we're going to return M0 of S. So we're going to fail on and return that. I don't need curly braces here. And then that ends the for loop. And then we're going to return M1. Oh, we don't even need to return M1. We return R because it already is successfully matched. Okay? Let's try it. Seek. So you have to say CHR A CHR map. No, you can't do that. You can't. Strings don't have a map function, but you can say let's just do it the right way. I'll think about too many things on my head in the moment. It's probably not easy. It's easy to do this, but We'll just do it the hardware right now. CRJ, CHRB, CHRC, on X. That should fail, obviously. PS is not. Okay, I lost something. Okay. This needs to be a list of things. There we go. That failed. If we say ABC, that should work. If we say ABCX, that should work, and CH should be X. And maybe I should just copy and paste all this stuff to the, like, into maybe another buffer so that I have the tests that I think doc tests. And then if we say, so that should work. And then if we say end, that should work. But if we put an X here, that should fail. I'm going to copy all this and I'm just put it in a thing called tests or something. Okay, so unzoom, parse code tests. JS. Okay. I might as well take these as well. I'm not going to scroll back and get all of them. But that does not seem like the thing I just. Yeah, there we go. You got too many different kinds of copies and pastes in Emacs. Emacs copy and paste, Emacs copy and paste. My own clipboard. Okay, what's next? I guess we go back to this thing and find out what CHS is. So sequence. We did sequence. So, I didn't copy what sequence is. That sucks. Sequence, match a sequence. Match all patterns in sequence. All right, so I'm just gonna do it like this. Oh, that's fine. 3 lines, but whatever. I can do it like this. It's kind of ugly. Whatever. Yeah, like 97. Not actually that bad. 95. I try to keep things under lines under 65. 64, whatever. Oh, we can remove this. Actually, I don't mind this. All right. That's what being a K programmer does. Many years ago, I went and looked at I wrote some code that was very terse like this, and I said, I will come back and look at this in a few weeks and see if it's incomprehensible to me. And I came back, and it was not incomprehensible, so I decided to keep writing this way. Again, future employers, I will follow whatever spec you want, whatever coding standard you like. All right, so alt also takes a list of patterns and returns a function from S to S, state to state. And what is it going to do? So alt is going to do another loop. Well, no, it's not. It's going to say, it's kind of the opposite of this. So let, I think we need to do the same thing. Let r equals s, and then for, oh, you know, but one thing we don't have to do is this. We don't have to do this. For p of p's. Yeah, look at that. Can we cram it all into one line? Yes, we can. Do it. All right, so now I got to check that all those tests work again. Because I didn't write a test suite. Oh, PS is not a function. P of, right, so it's even shorter now. Ah. And it all fits on one line. All right, so there we go. That should work. And then what did we do? We said ABC. So that should work. And then we put a end here. That fails. And then now it works. Okay. Curious what we keep putting end to end. I think that kind of undefined behavior, but it should work. Okay. Okay, so now alt match the first match, if any, match, try each one in order. See. Use the first, not use, but I say accept the first matching pattern or fail. All right, and so this is going to call alt and it takes these. And so what do we do? Slightly different here. We're starting over each time, so we say we take the original state. And set r equals p of s, and if that, then we return r, else get to the end of the loop, and we're going to return s. We're going to return m0 of s. Okay. I never did go back and do the joining all the, wrap these, but I'm going to do that in a second. There's a one called lit that will shrink the implementation of this. So it's a literal sequence of characters, which just combine it's specifically so you don't have to write this. Anyway, so let's try alt. So A or B. We haven't done not yet, have we? Right, so have we? Ah, did I just lose my? Okay. So A or B, and then we're going to do on, ABC. So that should work, right? Because A is one of the, PS is not iterable because we didn't put these in doohickeys. That worked. And this failed. Ooh, R is not defined. The MBS. None of them match. So that failed. This passes, and then we'll put an X in front of it, and then we'll change one of these to an X. And make sure the second one works. That works. I guess a better test would have just been DAC. Fails, but if we put like end in here, end, it should work. Which is exactly how you define optional. So opt, I don't know if that's the next one on the list, but that's easy to do now. We just say, takes a pattern, and then goes from state to state. And the pattern is, we're just going to say alt. Oh, we don't even need it. So we just say alt, P, or end. Except that's not how to do it. So then we can say opt character X. Oh, hang on, this is wrong. So then I lost it again. Oh no, I was on clipboard. Opt character X on anything. Although that should pass, but not consume any characters. Yes. And if we put an X on the front, or if we change that to H, there we go. It consumed one character. Oh, did not pass. Oh, okay. So right. So it's not end. It's empty. Emp is not defined. It's the very first thing I defined. Emp equals M1. There we go. All right, so what was it? Where to go? Opt is just alt P or end. Opt optional. So the next one should be repeat. Which should be emp, any, neg, and paired. Oh, lit. Okay, so we finally do lit. It doesn't matter what order you do these things, except for the ones that are defined in terms of each other. So let's do lit. So lit ABC should match ABC. So on ABC, this can fail because it's not defined. So lit is going to take characters and return a parser. And the way we're going to construct that parser is we're just going to say for, I mean, we could like duplicate the logic of sequence, but I think what we need to do is just say, that's the problem with this. So array array from, I believe is the way you take yeah. And if we have an array, if we have like a list, oh, how about we do this? CS equals array from there, and then we say array from CS. Oops. Then we get the same thing. Okay, which is different from, which should be a different array, I think. CS2 equals. Oh, but we didn't call it. I think they're different, but we'll find out. So CS2 equals, there we go, and then CS. Oh, they are the same. Okay, well, how about if we say, can we do it like this? We say hello. Does that work? Oh, it does. Okay, so we can do that. We can do this, the splicing syntax. I want to call it a splat. Opt is pemp. You copied the first wrong definition. Thank you. Opt. Thank you so much. I really should be using test suite, but the point of this is to make a test suite. And I'm running into the problem that well, the way my tests work, you have to talk to the they're language neutral, so you have to talk to the underlying program, and so you need a program to do that. So this video is meant to be like how to write a parser in like 10 minutes or whatever, and that's why it's like so terse and quick. And that's not gonna be 10 minutes, but like, you know, quick. It's gonna be very, very quick to write this. I want to do a speed run of this, basically. So that I can get people up to speed so they can write the parser, and then if you know, I'm not really fond of tutorials most of the time, but this is bootstrapping. So. And of course, I'll just provide the thing as a library too. Okay, so what is the point of this? Then we will say I'm just going to kind of write this in place and test it out with hello. Right, of course. So we're going to say yes. And then we're going to say dot map CHR, right? So then if we say sequence of this, we need this. That's our parser. So P equals this on banana. That should fail. And if we say hello, it should work. And if we say hell, right, it failed. It failed completely. And if we say hello, hello X, it matches and leaves us pointing at the X. We're good. Okay, so is this the implementation of the word is lit. No, hang on. It's CS, and then we're going to take this. That's it. Lit ABC on ABC should match. good to me. Take the whole thing. Like, okay, lit rep. Okay, I'm gonna make a new page. More parser combinators. More. Yeah. I put two of them there. More parser combinators. All right, so we need rep, orp, not, and set. So rep is going to repeat p one or more times. Orp is repeat p 0 or more times. So optional repeat. Not is repeat match any character except. Is it not a character? No, that can't be right. It's more advanced than just a single character. Otherwise, consume one character. Okay, so one input. Match any character unless p matches. And you can see that that was pretty simple. So we just say not is going to be. I bet this will work. Any so it's going to be p. It's going to be neg. So it's going to be a sequence. This is the J version is all postfix, because that's how you have to write. Higher order functions have to be adverbs or conjunctions. And they take postfix. So sequence of neg p or any. Okay. Great. So we look ahead and we say it's not that, and then any. Okay. This match. Okay. So right. So let's try it. I know I skipped it. I just happened to see how simple it was. So I just so say not. How about we say not lit banana? How about we say cat? And then on bat. And that should consume the B. Yeah, and so moved it to the A, match one. And if we say cat bat, that should not consume anything. Right? It's on the C, it says 0, yes. Good. Cat sheet. That should match. And what did it match? It matched the M. Matched the A. But one thing I like about this is that you know, you can add things to, like when we go to add the like the like we don't see the M anywhere, right? And I think I screwed that up. Hang on. We don't actually see that we captured the M, but when we go to build the tokenizer, you know, all we have to do is say, you know, start a, you know, we wrap the sequence in something. We say at the start we're going to set the mark, and at the end we're going to compare the mark, and if it matched, you know, then we extract that much, and so we can just add stuff to the state, excuse me, as we go along, because we use these little accessors. All right, where am I at? I skipped over rep. What is rep? I mean, I know it's repeat. All right, so what this is saying, this syntax right here is basically a do while loop. So the very first thing we do, this is like M1 in mind, so I'm just setting the match bit to 1 on Y, on the state. The names in J have to be Y, and U is the parser on the left. So this is mapping a parser to a parser. So U is the initial parser, and then now everything here is the parser that we are returning, and Y is the state. So so we set the state to 1, and then this says loop until do whatever's on the left of this stuff over here. Do that as many times as possible until it stops changing. And then we say do this while the match bit of the input is true, or do it if the match bit is true. So do it n times. Literally, this says do this 0 or 1 times based on, you know, match bit is going to apply the function to the input, get back a 0 or 1, and then do it 0 or 1 times. And then this underscore, it means infinity. So do it infinity times until it stops changing. That's the special overload for infinity, because otherwise it'd be an infinite loop. So if it stops changing, if the output of the function stops changing, then you're done, because you reached a fixed point. So you could also think of this as being like the fixed point pointer. And so basically, this is so just keep looping until it stops matching. So it's set the match bit to 1, and then while the match bit is true, keep looping. And then since we forced it, so now we have to say, has the index changed? So this is a fork. So we're going to take this input, and then we're going to look at so, right, we're going to extract the match bit. So hang on. No, I see. Sorry, this is a setter. This is a fork. So this is going to happen. This is the input to MB, so on the right, and then this is the input, the other input to MB. So we're going to say and this form takes this is so complicated. This was meant to be a J lesson, but take the index of this thing on the right and the index of this thing on the left, and then in the middle of those two things, apply the less than sign. So basically, has the index moved? And then the answer to that question is how we're going to set the match bit on the thing on the right. So right now the match bit is 1 because we forced it to be 1. But if it hasn't moved, then this will be 0, and that'll force the match bit to be 0. This is a setter. This is why it's a dyadic thing in the middle of a fork. It's kind of nice. In fact, I want to do a whole video for like this in J, this pattern, because I think this is something, for all I know, other people do it, but I've never seen anyone do this in J. This is, I think, is my invention, my style. But I'll you know, that's why I'm going to make the video and see what people think. Anyway, so then, right, so this whole thing is a dyad because the initial state here. And so this would then produce a new copy of this, which has either changed or hasn't, and that's it. And then just set the match bit to whether the index has changed. So we could do the same thing, and let's just translate that to. I'll copy this over, and then we can see what it looks like before and after in JavaScript. I'm curious if I can express this nearly as tersely, and maybe you shouldn't express it nearly as tersely, but I don't know. We'll see. All right. So what is rep? Rep takes a P and returns an S to an S, and I'm going to say so to get the initial value, we need to preserve that, and then we do some series of operations. So again, we have to do let R equals S, and then we're going to return we're going to modify R and say right, because we want, like, if R is advanced, we're going to keep that. Otherwise otherwise it's going to be identical to S, except for the match bit that we're changing. So actually we can say this is M1 of S. That sets the match, that's this part. And then at the end we're going to return MB, and that's going to be IX. This part, this is called under. It's dyadic under. Not dyadic under. Top. What it's called. It's called a top. If you put a dot after it, would be under. That would undo it. That would undo the index. Hey Ayush, welcome. I'm translating J to JavaScript today. All right. So anyway, not wanting to write this right now, this little and sign, I'm going to say, I'm just going to write the translation of that, and that would be IX of S, the initial state, is less than IX of R. So if that's the case, then we have advanced forward, and so that's going to set our match bit. If we haven't advanced forward, then R is the same as S except for the set, and then this undoes the initial version. Okay, so now we have to do the thing, which is this. So that would be while MB of R is equal to P of R. That should match and consume one token. Oh, rep is not defined. What? What do you mean it's not defined? Oh, because I okay. Sorry. There we go. Oh yeah, because that should have said function. Okay. Not bad. All right, so it did. Oh, okay. This needs to be that, except rather than doing that, I'm going to go way back up here and redefine MB. Oh, but I can't. Yes, I can. And I, yeah, if that returned undefined, I'd be in good shape. Problem is, it's a getter and a setter. It doesn't matter. I'm doing all this to save like one. Or I could just make a new. All I did was I added a plus sign around that to cast it to an integer, so it no longer says true. It says 1. I could make these getters and setters like have a validation function or something in there. Maybe it might make sense to do that. Add some kind of validator type coercion. That's not how you spell coercion. It is how you spell coercion. Okay. Or MB true. All right, so then it should also match aardvark. And you see it matched both the A's. And of course, we should test that it does not match on potato. Good. So a little longer, but not too bad. Still one line if you cram it. Okay. And I saved the test, right? Rep. Orp. Orp is easy. Orp. That takes a parser, and it's just going to be right, that should work. So now all of these should pass, but some of them should consume different things. So we say orp pair A on apple should match, consume an A. Aardvark should match and consume 2 A's. And then potato should match and consume nothing. It does. That's orp. So that's the star. It's called the Claney star. Or Claney. Claney plus sign that you use in regular expressions. And then opt would be the question mark. Claney question mark. And then sep. Okay, sep is to match a sequence separated by what do I call it? By delimiter D. Pattern D. So then sep is going to take which one did I do first? What's the left argument? It doesn't matter, but one or more U separated by V. Separated by V. Match. Oh yeah, one or more. So okay, let's write it that way. Match one or more P separated by D. Pattern. Both are patterns. So then that would be a sequence. See if I can do this. So sep, it takes P and D. Sorry, sep is equal to P and D. It takes P and D and returns a sequence consisting of E followed by as many repetitions as you like of D of the sequence D followed by P. So then we'll say sep. So we'll do like any. I'll say rep. I'm curious what this does. This is not what I intended to write, but so anything followed by like trying to see if it's greedy or not. Oh, how about this? We say, I think this is going to be greedy. We can do this right. We can say anything followed by a character, comma. And I think what's going to happen is it's going to consume everything. I think it's going to consume the whole thing on A, comma B, comma C. How about A, B, 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 and then C, 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 C. I think that consumes the entire string. Oh. P is not a function, okay. Hang on. Rep any is not a function? It is a function. I get if I ran this whole code again, maybe I should do that. Let's try to, let's load the code. I don't know how to load the code if I don't. That's might. But if I made any mistakes, I originally conceived of this video series that I'm making as a book, a CS book. Okay. This was a joke. I guess you say how do you just run node and then interact in the node run and then interact? Oh, dot load. Okay. There we go. Okay, well, now I learned something. So now if I run this, I should get a stack trace to tell me why. Oh, what? What? It's still in the REPL. Hmm. All right, well, let's put it back together piece by piece. So we'll say P is going to be rep any P match. Sorry, P match. P on A comma BBB C, right? Worked and matched the whole string. Interesting that the match bit is now over here. I'm not sure about that. I'm not sure why that happened. Okay. That matched. Ah, so there's a problem with ORP. And the problem, it's not a problem with ORP. The problem is that this is what it should be. Yeah, I don't think you can see what. Okay, I don't know what that means. Can we go 79? 79? Rep. So orp. I did test orp, right? Yes, okay. What is P? P is rep any. Oh, okay. If I just put this here, maybe I'll get a. Let's just start with this. Sep any chr comma on a comma b comma c. P is not a function. What if we say rep sequence any and chr that? That worked. Okay, that's what I expect. We say orp. That worked. Got the whole thing in a sequence. That worked. Call P0 equals this thing. I feel like maybe I'm leaving out the sequence. I think I did. I think that's exactly what I did, didn't I? Did I? No, I didn't. Oh, it isn't a function because I put this in brackets. You don't put that in brackets. You put this in brackets. All right, let's screw that up. Sequence contains things. The sequence itself, but orp does not contain. Orp just takes a pattern. There we go. So I had bracket right here, and I shouldn't. All right, so that. Come on now. No, I had a bracket right inside the orp. Okay, so now this should work. So let's see. We say. I'll just do it again. So we'll match on sep. That's going to take any separated by chr comma. We'll say on a comma b comma c. That should match, consume the whole thing. Yeah, ch undefined means it made it to the end. And then I was just curious what happens. So if we say b here, that should fail. Oh no, it doesn't fail, right? Because it matches a comma b and then leaves me at the next b. That's right. That's correct. But if we say rep any, that's going to match the whole string. Yeah, all the way to the end. but for the wrong reason. So what we want to say is not comma match anything that's not a comma on that. Ooh. But you can't say that. You have to say not character, comma. And that matched. And I think if I were tokenizing, if I had the tokenizer working, I think it would extract the actual tokens, then this would tell me the difference between those two things. I believe those two things are different, but I can't prove it right now. Let's get rid of this. These two should both match, but tokenize differently. If I had tokens, if I had Tokia. Okay, we're basically done with this. We've done all these, and then the next one is to build these things. It's 1 o'clock here. I'm going to stop. But just as a hint, the idea is that now we will add the parse state to this, and basically token is going to say, well, at the start of this match, record what the where the position is, and record that in the mark field, which is MK, which has just been -1 for now. And when we get to the end, if we matched, then look at the index and see how far we've moved from the mark. Which I guess really maybe we don't need the mark. Maybe we don't need that. Maybe because you have the index of the original. I'll have to look at that and see. But anyway, basically, if we move, we did the same thing with rep. We looked to see at the previous index to see if it's moved. But the previous index is the mark. Yeah. Anyway, but and then you just extract that string and stick it into a tree builder, which I've already done in the Implish parser. But this is a good stopping point. So then symbol is just the same. Is just you give it a string and it it just takes that string, wraps it in lit, and then that's the then passes that to toke. So it's just lit toke. Sounds like a drug reference. Zap does the same thing, but it moves the mark forward, but removes the token. Oh, I wonder if maybe the mark is there because I'll have to study why the mark is there. It might be there because of nesting. I'm not sure. Maybe not. I'm not sure. Anyway, element basically says that if this matches, create a node, and as we're going along, we're gonna build a tree. So tokens have to be inside of. Well, do they have to be inside of an element? No, because your tree builder has a root. So element just calls node to create a new node in the tree, and then we already have a tree builder that does this. 2 lines of code in JavaScript, 3 lines of code. Adder sets an attribute on the current node of the tree. So the trees are like XML trees, so they have a tag and attribute and body. In this case, it's just a list of other nodes and tokens and other nodes. So when you type toke, it emits it into that tree builder. And then if you match an element, then you get to the end and you and this is all immutable except for the top layer. I might have to make. So yeah, so I separate the tree builder from the tree state, and I think maybe I might need to do that as well. So rather than have the tree builder be an object or a class in JavaScript that's mutating its state as it goes along, it might have to I might have to make it functional, so that you just separate the state and then you operate on the state and then you make a new copy of it, um, which is what gives rise to like append and take, so push and pop on those um, things. So basically, zap is gonna say these are like getters and setters on the struct, but they actually also push and pop things. So push, pop, or just apply a function rather than just setting things. Getting. Yeah, it's pretty easy. But like I said, it's now 1 o'clock, so I'm going to stop. And yeah, that was it. I thought that was fun. I thought that let's look at this. Like if you strip all this stuff out, this is pretty terse. This is not stripped. Just make sure we have the same version. Yeah. If I strip all that out, this is redundant. That's it. 29 lines of code. And it could be a whole lot, you know. I don't know. I don't think I would make it smaller. 29 definitions. That's pretty decent. For a parsing library. And how long did it take? 3 hours to go through that. And there were lots of mistakes. And I bet if I planned it right, I could knock that down significantly. It'd be nice if I'd love to get this down in like under 20 minutes. I never call forward directly, so maybe forward M is like the only thing I really need there. Like I could probably merge those two together. Save a definition. That is hard to look at though, isn't it? But you know, in the right context, I think it the context is you have to read the paper and you see the math behind it. Like what is, I mean, I call it math, but like yeah, like Trainees papers are math papers, computer science papers. I haven't read his papers, but I mean, I know that like prep or like regular expressions were built by reading his papers or whatever, and then this is just like parser combinators that, you know, just a functional version of those kinds of things. It's not the JavaScript that came out on day one. What's his name? Spent 2 days writing JavaScript, but I think it's turned into a pretty nice language where you can be mathematical. I would not want to read this without comments, but if I had a key, I'm okay. It's not even that. It's just hard to look at with all the text there. But if you look at them in isolation, one at a line, one line at a time, it's not that bad. Like I can, it's just my eyes are not used to looking at it. I imagine other people find this ugly as well. Maybe I'll take a screenshot to post on Twitter just to scare people. All right. All right. Thanks so much. And yeah, this is definitely going to be this was a rehearsal. There will be a better version of this in the future. And of course, there's going to be test cases, and this is going to be a challenge to make this. I have to figure out how to write the test case using my test runner because in a language neutral way, because I don't know how to do that yet. And for everything else, I know how to do that, right? Because I'll have but maybe this answer is the same. Like you just use a bootstrap parser for the tests, and then the testers will do remote function calls, procedure calls. And then the question will be like, how does that work? Well, do this course, and then you're using it to test it. And the answer is, if you don't want to do that, well, you can just rely on hope that it works. Because anybody who's a pioneer who wants to run this the first time is going to have to do like what I just did in this video. And so that's why I don't want to give them a 3-hour video to watch. I want to give them a quick video to watch, and then give them the test cases to back it up. Yeah, this was not painful at all. I had one thing where I where like the ORP where I missed the bracket, and I couldn't get a stack trace. Even this right here, like that's annoying. But the other idea I want to do, which I need to do, is to do an interpreter for this. So rather than doing parser combinators, just have the exact same words, but build a data structure that we can then walk. And then you have like a little virtual machine that walks through that data structure. And I'd like to do that because at some point, because it'll be much easier to do that style inside of my V4 virtual machine. And then I can get the parser combinator or parsing engine running on that virtual machine on V4. And then rather than having to port this to a new language, you can just port B4, which is much, much easier. Much, much shorter. And comes with the debugger from the start. Whatever. Anyway, yeah, that's it. Thanks for watching. And